Hello and welcome to the webinar CFD, Color for Directors, Answering Difficult Engineering Questions. My name is Boris Marovic. I'm the Technical Manager for SimCenter FlowFD products, and I'm guiding you through this webinar today. But let's first have a look at the agenda. We're going to talk about what is CFD, and that it sounds quite awful and complicated. Why do we need CFD? And okay, but what does CFD actually do? And then we're going to have a look at the conclusions before we come to the question and answers. So what is CFD? Well, there's some results for the acronym for that. One would be Color for Directors, as the title suggests. There's also Contract for Difference, which is more a financial term, the CFD trading. Corporate Finance Department. I mean, every mid-sized, larger company has one, but we're not going to talk about them. The Chicago Fire Department, although they deal with fluid as well and heat, but luckily we don't have to deal with them today. And the cubic feet per day, which is a measure we could use, but it's not quite the size that we're looking into. What it actually means is computational fluid dynamics. So basically calculating what the fluid and the heat does. Yeah, it sounds quite complicated, especially if you're not a genius in that field and understand all the equations. So the math behind it can be quite complicated. It looks somewhat like this. But there are different levels of CFD. For some, you need to understand CFD very detailed, and to understand the math behind it, you can program your own equations into the products. But they're more for the analysts, for the real CFD experts. There are other tools also for designers. Just like you have CAD embedded structure simulation tools to already test if the structure would last, this is also available for designers in the CFD space. And of course, there are the experts out there who really understand CFD. And if you have some in the company, that's always good to have, because they can answer your questions. They can help you with difficult issues. But even if you don't have CFD experts, despite the complexity, management experts really advise small as well as medium-sized companies and the big ones to not ignore CFD just because it's complicated in nature. On the contrary, you should really use it. So why do we need CFD? Our design works without it as well. True, a horse works as a mobility solution as well. But if we look at what allegedly Henry Ford said, if I had asked people what they wanted, they would have said faster horses. So here's why you should use CFD. Are you sure that you can't optimize your products any further? Yes, it works, but does it work to its best? Can you be really competitive, beat your competition in terms of efficiency, performance of your product? Or are you just assuming, yeah, it works, we know what we do it, and we always did it this way? Experience is not equal full understanding of your product or the understanding of new methods and technologies. For example, if we look at computers, what we do today is we work with computers, notebook, tablets, phones, digital devices all over. And we're quite experienced in how they work and how they perform. But with the new technologies such as quantum computing, the old principles don't just apply like that anymore. So new technologies might require you to think differently, to do simulation, but also just because you know how things work in general doesn't mean that you can't optimize it. You should use CFD for any product. It doesn't matter if it's a valve, if it's a pump, because maybe there's a new idea you want to test. Maybe there's areas in the valve you never looked into because you only knew it from experiments. And experiments are just a black box. You can't look inside of the valve to see what's actually happening there. With CFD, you can actually do that. Just to give you an example, I was once working with a customer. They design large forms where they put in the carbon fiber layers of composite designs, composite structures, and then they put them into autoclaves, which are basically large ovens where they bake the carbon fiber with a resin to harden and get the final product out of it. Now, they have an autoclave, which is a large square room where the door is here at the top, here, and they have two walls on each side where the flow comes in. And what they were expecting is that the flow comes in like this, and since it's symmetric, they would expect two vortices separating the room in the middle. But I said, okay, we need to understand exactly how the flow works. If they stack in their products in there, they want to make sure that it's equally heated, not that one part of the product gets too hot, it's burning, and the other parts are too cold and not really getting done. So they did a simulation on this autoclave with the SimCenter FlowFD, and this is what they got. So they thought the simulation is wrong because this is not natural. It's a symmetric room, should have symmetric vortices in there. But they said, okay, let's do a test. So they put in some poles with the warning tapes attached to it, so they can actually see how the flow is circulating in there. And what they got is really this. They didn't expect it. So they expected really to have a symmetric flow as well, so two vortices in there. But reality is sometimes behaving differently. That's the reason why you shouldn't just trust on, we know how it's done, we have experience, because there's some parts in your product you can optimize. Although the experience works, you know how things are generally done, there's still ways of over-designing your product massively. So even if you have a plan, everybody has a plan until they get punched into the face, is what Mike Tyson said. So there are different methods. Of course, the first one is rule of thumb, experience or handbook rules. This is how you can get started with things, but you also massively over-design your models, and they're not optimized at all. You could also go and say you want to do hand calculations, where you still over-design the models because hand calculations are not that detailed and still not optimized. You could also do experiments and tests where you get somewhat oversized and the good design comes over time, but you often don't have the time nor the money because they're quite costly to produce a lot of prototypes and constantly test them. It takes time and money. And then there are simulations where you usually get very well-sized product with very good design and in a short development time and costs. And an additional focus would be then to add optimization to the simulation. So you get a perfectly sized product, a perfect design within the constraints, because it doesn't matter if you create the perfect heat exchanger and the geometry simply is way too expensive to manufacture, even with 3D printing. Here simply the costs don't outweigh the benefits, and you have a short development time and cost. All these 5 types of methods are all reasonable, but you don't do either or. Usually you do all of them in a certain order. So the rule of thumb is usually what you start with. If you have a new product that has to be developed, you go and say, okay, we need that type of valve because this is ideal for the kind of target we want to achieve, either flow regulation or pressure release or anything like that. This is basically the handbook, rule of thumb kind of experience that you have. Then comes in hand calculations, such as, well, pressure drop between inlet and outlet depending on the valve coefficient, which are usually this way. You can calculate roughly, depending on multiple parameters, which range you will go, what type of diameters you will need, what type of components, how big they should be. So this way you can start with creating your first CAD model. Once you have that, you can run the simulation to see how close you're actually getting already. And then you can do multiple iterations to optimize it, or actually really using optimization software, for example, SimCenter Heats, or the SimCenter FlowFD Heats embedded module. So this way you can optimize it either automatically or manually to get a more optimized geometry, optimized performance. Once you're done to the point where you say, okay, this is how far I've gotten, this is now the product that I want to release, let's go into testing first. So you go into experiments and test onto the test rig and really see if it performs the way that you were simulating it, if it withstands the structural loads, withstands all the parameters that it has to withstand in reality. If not, you can still go back to some optimization simulation, do some more cycles, but this way you reduce the overall test cases and prototypes you have to do, and therefore reduce the cost. Some of the reasons for CFD simulations and why they should be done. First, of course, you want to stay competitive by failing early, failing often in order to succeed sooner. This comes from Tom Kelly from IDEO. IDEO was the company that initially designed the first mouse for Apple. What that basically means is you want to do simulations early in the design phase, because here, if something goes wrong, it costs the least amount of money to fix it. Because here you have the first design, you do testing only virtually, so there's no problem there in changing anything in the design because you're still in the CAD design mode. Once you manufactured something, once you went into production and delivered it to the customer, any failure will be much more expensive. So you want to do these failings, these tests, very early in the design cycle. Failing often means testing a lot, testing new things, testing this, testing that. You can experiment here all virtually, so there's really no harm done. It's all just virtually. And then once that is done, you can go into manufacturing. Or stay competitive by build, measure, learn, repeat. The lean startup method. First you build your CAD model, then you measure or simulate it, then you learn from what went wrong, and repeat it by improving your geometry, simulating it again, learn from it again. Doing this a lot of times helps you to stay lean because you're doing simulations quite early where there are no real cost involved compared to building prototypes. And then stay competitive by being innovative. Of course, you have to be innovative in order to stay competitive against your competition, which is certainly not sleeping. And the better you can do these tests and experiment with new ideas, the better you can be innovative, because you can test new ideas, something that you have never tried before, where your experience might not help you because it's something completely new. You have no experience with it. By doing simulation, you can learn from that without doing prototypes, without doing costly experiments, and learn from that. So CFD helps to be innovative, experiment early, fast, cost efficient in order to be lean and agile. Yeah, I know the two buzzwords, lean and agile, but it really is this way. You stay lean because you're doing this cost efficient virtual prototypes, and you stay agile because any change, anything that happens, you can quickly change something, run the simulation again. Even if the management says, hey, we have to, increase the volume flow rate for the valve for the final design, it's something quickly done in parametric CAD tools. You can quickly adapt to any changes and therefore stay agile. So let me ask you, how many product-related decisions have you been forced to do blindly? With simulations, that wouldn't be the case. So what are the others doing? A study conducted by engineering.com showed that 22.7% of the participants of the study said they do simulations daily. 14.4% said at least once a week. So that's 1/3 of the participants doing at least once a week, if not more often. 70.3% perform the bulk of the simulation in-house. And 78.9% run simulations on their workstations. So it's actually one of the myths that simulations have to be done on clusters. Most of the interviewed persons here were doing simulation on their workstation. And the top 5 reasons for primary reasons for simulation were 70.1% optimized design. So really, design is the optimization goal. 68.9% design validation. So once you design something, you want to know if it works. So you want to validate, is that design actually performing the way that I have envisioned it? 59.7% failure analysis. So you want to test if things fail, or when they fail, what happened? Where do they fail? Before you go into any test rig to experiment with it. Or worst case, having the failure at the customer side. And 43.5% are looking for product design innovation. So really being innovative, being ahead of the competition. And 43% reduce risk and liability. If something fails out there in the world, burning down a house because the heat exchanger exploded or the gas stove exploded, anything like that, You don't want to be reliable for that. So that's why you do simulations early on. You can structural simulation, fluid flow simulation. All these simulations are in order to find flaws in the geometry, in the design, to really optimize it, to not cause too high temperatures, not cause things to burst, explode. You want to make sure that what you design will work, will be reliable, not just in the first few months, but also over time. So lasting for a long life. So, okay, but what does CFD actually do? Well, CFD solves mathematical equations that describe how the fluid flows. It might be gases or liquids, like you can see here in aerodynamic cases, or liquids like non-Newtonian liquid plastic in extrusion or injection molding and stuff like that, as well as heat and heat transfer from conduction, radiation, or convection. You can see, for example, the rays in a headlight where the bulb is emitting the rays, and how that basically will heat up the components because bulbs are quite hot, but also they have natural convection above the bulb, or the conduction from the bulb socket into the housing, into the fixture. The chemical components that react either in electrochemistry, like in batteries, or in combustion, like in this example here, we have a household gas stove burner. In general, what you do with CFD is you're usually interested in pressure drop. That might be in valves, in filters, or some ducting system, piping system. You want to record the fan curve, the pump curve. You want to see how much head the pump delivers with your design. Heat transfer. So every electronic device or every device that works on has some friction, will cause some heat losses. Or if you have hot fluids that run through pipes, you want to see if the pipe on the outside reaches below a certain temperature that you can still touch it. You have to put insulation around it. All these kind of problems with heat transfer, no matter if it's electronic related, heat losses in electronics, or through friction, like in a braking system, the braking disc. All this can be handled with CFD for the cooling, or if you want to heat something up like your flat. Mixing processes. Typically processes that you have every day is when you get up in the morning, go to your faucet, open it up. You want to get the right temperature between the hot and cold water. HVAC systems, when you get into your car in the winter, you want to have it at a certain temperature. All these mixing processes of different fluid temperatures, different fluid types to get the right combustion mixtures. Flow fields that can be around buildings, inside duct systems. So you want to see that the two ends of the ducts have the same velocity, such as in a HVAC duct in a car, or the flow field inside of a pump. You don't want to have dead pockets where the fluid is circulating, or you want to have the flow field around a fan, an object like an antenna, a building, aircraft, or a car. And from that, of course, also the forces on an aircraft and car, lift and drag, or the pump, where you get the forces on the pump impeller, which results in the torque of the pump, where you can then decide on how big the motor should be that drives the pump. Forces on buildings, or the flow between the buildings, how much the force would be onto a person walking there. So there are a lot of simulations in different fields, but those are the typical ones that people are interested in when they do CFD. Yeah, the industries are really wide. Automotive, transportation, aerospace and defense, consumer goods, electronic devices and semiconductors, medical systems, marine, industrial machinery, and energy and utilities. All types of industries, everywhere basically there's some flow or some heat that has to be get rid of, or you want to get the right temperature, heat it up or cool down. Now, you might think, okay, well, CFD is still kind of this high-end topic. That's not quite true. Of course, there are the expert tools that can do a lot of things, like droplet interaction and really complicated combustion cases. But a lot of these examples that I mentioned before, pump, valve design, electronic devices that need to be cooled or heated, stuff like that. All of that really can also be done by designers. And SimCenter Flow EFD is designed from the ground up for the designer, and therefore multi-CAD embedded, the only truly multi-CAD embedded CFD software that is usable from designers. So it's embedded in Siemens NX, Solid Edge, PTC Creo, and CAD V5 from Dassault System. Depending on what your preferred CAD system is, FlowFD is embedded in that, and then you can do your simulations in the design stage already very early by non-CFD experts. All that your engineers need to know is, what is my product doing? What are the boundary conditions? If I design a pump, I know that I want to design it with a certain head. If I design a valve, I know what the inlet and outlet pressures are. These parameters is usually what the designer knows, because that's what he designs the product for. Those are the boundary conditions that you have to put into the software, and the software does the rest. Now, you're wondering if CFD is really difficult. An Engineer.com study showed also on the question, why aren't simulations run more frequently? Well, 40.5% said because they didn't have enough training. So the products they used must have been quite complicated in order that they need more training, deeper training in order to really be able to do simulations. 40% said it's too expensive. And 24% said simulation programs are hard to use. With FlowFD, I can promise you, training is done within 2 days. Usually, if it's an individual company training, it's the first day, a simple example, mostly a tutorial model, where we show you how the workflow through the process is. The second day, we often work on a small model of yourself, a small project where you can learn how to set it up, run the simulation, and get some results at the end. We had customers that went out of the training having first results compared with experiment, which matched. Too expensive? Yes, there are products, of course, they can do a whole load of physics, really multi-physics, interaction, and so on. These products can be quite expensive, but they're often for analysts where they have to go really deep into the physics. For the designers, they want to know if the product works the way they designed it. Pressure drop, heat transfer, and so on. The things that I mentioned before. And of course, therefore, you don't have to buy a Lamborghini. And then the simulation programs are hard to use. I can guarantee you FlowFD is not hard to use. If you don't trust me, here are some of our references from customers. For example, Paul Henry Matat, the lighting expert, previously worked at Renault, now he's at Volvo. Once said, one thermal engineer can be over twice as productive with FlowFD because they're basically using the CATIA embedded version of SimCenter FlowFD. Another customer, Hidebumi Takahashi from Mitsubishi Materials Corporation in Japan, said, since we have no specialist CFD expert, our designers take care of the simulation analysis. SimCenter FlowFD is what they use inside of their preferred CAD system, which in this case is PTC Creo. Another customer, Klaus Olesen, a thermal design specialist at Danfoss Drives, I have another example from him in a second. He said, I can dip in and out of it all year with minimum effort to pick it up again. And Fumio Yusawa from Seiko Epson, he's a CFD specialist with experience for 20 years. And he said, I was amazed by its simplicity. So CFD simulation doesn't have to be complicated. In fact, SimCenter FlowFD is built for the designer and therefore usable by designers. So for example, if we take a model like this is an IGBT. IGBT stands insulated gate bipolar transistor. It's basically a transistor, a switch, semiconductor switch. What it does is it switches on and off, either changing the frequency. For example, if you have a wind turbine and you want to put the power it generate into the grid, the power that you generate might be a different frequency as the grid is running, so you have to adjust the frequency. Or an electric car where the battery delivers direct current and the motor, the electric motor, needs alternating current. The IGBT is switching into a frequency so the motor can be driven. So these IGBTs, they need to be cooled because They're power electronics, they run on high currents and voltages. And for that, they have a cooling liquid opening here and the outlet at the other end. And you can see these knobs here, which are basically pins of the cooling cold plate. Now, pins can be of all types of sizes and shapes. So it could be looking like this, where you have just thin pins all aligned in a row. It could look like this, where you also have thin pins, but on a diagonal pattern, a little bit in a pitch. Or it could be fins, so small rectangular fins, which have different lengths or different distances, different thicknesses, and so on. So by your experience, you might say, okay, this is the better design compared to this one, we know that. But what about this one? How many do you need? How big should be the difference? How thick can you make them? How long should they be? There's so many possible parameters that you can vary with. Or your experience probably didn't tell you anything about that pocket area here, where you could implement here some guide vanes to spread the flow more, make it already using the first few pins here where there's currently low velocity. So there are a lot of parameters that you can improve by doing simulation that you were not able to do with your experience alone. Even with hand calculations, you probably wouldn't have expected this one, but more calculated on how much the heat transfer would be here. But then what happens if I have to put multiple of them in series? So do you put 3 of them like this in series, or 3 of them? Or do you stack them with different designs? Because the first one will be best cooled, where the liquid is still cool. The second one is the liquid already a little bit hotter, and you want to have an equal temperature over all 3 of them. So how do you stack them? And for this, simulation is much better used because you can play with parameters, vary a lot of design parameters, and really create the optimum. And ideally, use an optimization tool. Then you would get something out like this. This is a Pareto curve where you basically have tested a wide range of parameters: the thickness of the pins, the distance between them, the length of the pins, as well as maybe some draft angle of the pins. And you can see, for example, I put in here a limit for 10 millibar and 100 degrees Celsius. Above that, they will fail much earlier, and we don't want that. And above 10 millibar, well, we need a bigger pump, and especially electric vehicles where you want to have a longer range, you don't want to consume more energy for the pump as well. So we wanted to stay in that corner. And you can see the infeasible ones are the red ones outside of that corner. The feasible ones are the blue ones, and the optimal are the ones that are building that front here, the green ones. I can still then decide, do I want to go with lowest pressure, or even better, be on the safe side, have lower temperature? So this is up for the engineer to really make that final decision, which of the optimums he wants to use. And he can play with materials, with dimensions of pin sizes, shapes, patterns, and so on. So he has a wide range of possibilities. But even here, this is normal design ideas. I mean, this is not really anything innovative in this way. You would immediately think about pins or fins. What Klaus Olesen did from Danfoss Drives was really being able to use that CFD capability to test new innovative things where you don't have any experience, where you couldn't think of how that would behave. You would probably ignore it if you just work on experience base, because testing something completely new would cost a lot of time and money to build prototypes and get that experience. Well, with CFD, they started something completely new. They have also IGBTs here in parallel, where you have the inflow and the outflow. And for that cold plate, they designed something completely new, which looks something like this. So you would say, yeah, it looks like a labyrinth. So there's a long path through here, higher pressure loss. You have no idea how that will perform compared to pins and fins. So that would be something completely new. But not only that, they created a small gap on top of the labyrinth. And with this, they couldn't tell how big the gap should be. So they played with the gap size. They could play with a lot of parameters to find the optimum, because high velocity through here increases the cooling performance, but too big gap size will reduce it. Too small gap size will reduce it as well. So finding the optimum here was all done by doing CFD. If you want to know more about that, there's a video from him, an article as well as an interview about him. So all of that is what CFD actually can do. So let's come to the conclusion. What about CFD now? So CFD is not just colors for directors. It is an engineering tool to allow for gaining the competitive edge. CFD doesn't have to be complicated. Even designers can use SimCenter Flow AFD as a CFD solution. And CFD is an important tool in the product development process. And then CFD, of course, helps to be more innovative, make products more efficient and reliable, save development time and cost. And then, of course, you get to market faster by doing the simulation quite early to define your final product much sooner, getting to market faster than the competition. So with that, I thank you, and I'm now open for the question and answers.